Hello everyone, welcome back. This is part 5 of the electrochemistry discussion. This is Dr. Rhonda Kofelt, and this will be the last part of this discussion. And in this discussion we're going to talk about the electrolysis. So we've been talking about Voltaic cells, and now we're going to look at the electrolytic cells. And in these we are doing stoichiometric type things, and we're going to actually be plating. So if you've ever seen, chrome bumpers or flatware that's, silver plated or something like that, or jewelry that's gold plated or whatever, electroplated, that's what they're doing is what we're about to talk about now. So I want to go back to a slide where we contrasted the voltaic cells, which we've been talking about, which are spontaneous, which produce their own electricity, to these cells, which are electrolytic cells. And just remember, okay, that you are still calling an anode. An anode is where oxidation occurs. Okay, so just keep that in mind. Electrolytic cells are a little different from our voltaic cells. Number one, because we have to add current to it in order for it to go. So that would imply that we're pushing it back the opposite direction, right? So here's your voltaic cell that we've been looking at. It's our old buddy, the zinc and copper voltaic cell, where we saw where we were moving electrons from the anode to the cathode. Now, in electrolytic cell, notice this is just to measure what the voltage is, right? In electrolytic cells, I have a voltage source. Okay, I have a voltage source because it's going to draw electrons from the anode to the cathode. Okay, it's going to draw them from the anode to the cathode. And so it's written backwards from what we saw the voltaic cell as. And the main difference is this: because we have a voltage source which is pulling those electrons from your anode to your cathode. Otherwise, this would not work. Okay, this would not work. So electrolysis literally means breaking apart with electricity. And so you're using electrical energy to break the bonds in a compound. And it's done in an electrolytic cell. And a lot of times we use electrolytic cells to separate things from each other. For example, you can actually electrolytically separate water into hydrogen and oxygen. So we're doing the opposite of formation, right? We're taking something that we already had and we are producing it. And literally you're doing it in this electrolytic cell, capturing oxygen in one balloon and hydrogen in the other balloon. And that's just a simplified drawing of what an electrolysis would look like, or electrolytic cell would look like. Notice we have to have a power source though, and so we have to have some type of battery or plug it in or something. So we use the electrical energy to overcome that barrier, that energy barrier of the non-spontaneous reaction, pushing it really to make it occur. And so because we take water we can make water from hydrogen and oxygen gas, which is a spontaneous reaction. But if I want to take water and turn it back into hydrogen gas and oxygen gas, I have to use an electrolytic cell. So I had to make it do that because it is not energetically favorable. Okay, some applications of this. This is one way that we get metals from impure metals, or minerals, where we get them out of the ground. And they've got all kinds of stuff in them, and we can use electrolysis to pull those metals out. Producing hydrogen for fuel cells. This is one way we do it. You can see why that's such a nice, clean way to produce energy for cars or whatever. The only problem is when you put these two things together, they have a tendency to blow up. So we have to work that out. But if we can do that, we'll have a good clean source for fuel. And then also for metal plating, like I was talking about in the introduction, where we plate jewelry or flatware or car parts or whatever that we want them to be nice and pretty and shiny. So we generally give the current to the process in DC, or direct current power supply. Alternating current, the electrons don't they're not flowing consistently, and so it doesn't allow that reaction to occur. Some require more than the E of the cell says they do, so we have to have an overvoltage in order for that, because it is not a reaction that wants to occur, and we have to make it. So we are having to add voltage, and sometimes we even have to add more voltage than what it took for the stuff to come apart. Okay, so we either use a battery or a DC power source. The positive terminal is at the anode, the negative is at the cathode. Okay, and that's the opposite from what we saw before. An electrolyte, if you should have learned this long ago in acids and bases, was it can be a salt or acid or base, or it can be a molten ionic salt. Molten ionic salt means that it doesn't have water in it, okay, but it is heated to a point where it is a liquid. It flows like a liquid. Cations are attracted to the cathode, and anions are attracted to the anode. The cations pick up the electrons from the cathode and are reduced, and then the anions release their electrons at the anode and are oxidized. So you can still use your definition of anode is where oxidation occurs and cathode is where reduction occurs. So we've seen the reduction of a cation, reduction of water to hydrogen gas, as we saw before. Possible anode reactions, making oxygen from the water. And then oxidation of electrodes like copper. Graphite won't oxidize though. Graphite, is carbon. And so we can use that as an inert, but it's not going to oxidize. So the half reactions that lead to the least negative E cell will occur unless you have an overvoltage. And so this is just the picture I was showing you of the anode and the cathode, and how we are producing electrons at the cathode this time and pushing them back to the anode. So when this is a picture of kind of what we see in the electrolytic cell, you have the voltage source. Okay, you have an inert electrode of some type, like carbon, like graphite, okay, which is carbon. And then another type, and again, it can be graphite if you want it, or some other inert. The cations are reduced at the cathode, all right, and the anions are oxidized at the anode, right? So that's not new. All right, so you can still leave that. That's why I've stressed that so much at the beginning, because as long as you keep that in your head, you still got it. When we electroplate something, we're going to have whatever metal we want to turn into nice and shiny on something that maybe it doesn't cost as much, like zinc or a nickel zinc alloy. And then we take the silver, convert it to the ion, and then the silver ion will go to the surface of the other material, and it will actually deposit the silver on there. And this is because we're providing electrical force to make this happen. So the working piece of an electrolytic cell is the cathode. That's where your plating is going to occur, is at the cathode. The cations are reduced, as we said, at the cathode, the plate, and then they plate on the surface of that cathode. And the anode is whatever metal you're using. In this case, it's silver. You can use gold, you can use copper, you can use whatever. and that it oxidizes and replaces the metal in the solution. So it's giving you those ions to work with to plate to the other material. So in this electrolytic cell, how much you can make is related to how many electrons you're transferring. Okay, so basically your electrons in an electrolytic cell are your reactant. And the number of moles of electrons that flow depend on the current and the length of time. So how many amps, okay, and how many moles of electrons. So the ones that are, like the 6 electrons would give you more. It would give you more, and it would probably happen faster than things that only are transferring 1 electron. All right, remember this: 1 amp is equal to 1 coulomb per second. Okay, 1 mole of electrons is 96,485 coulombs. Okay, and Faraday's constant, that's what this is. It's really, Faraday's constant is 96,485 coulombs per mole. Okay, and Faraday, if you've had physics, you may have heard of him. He was in there with all the Teslas and all that. He was into electricity and current and all the things that you can do with that. So, all right. So when we're looking at this as a reaction, mainly what we're usually trying to figure out is how many grams of this precious metal can I plate onto this ring so that it will now look beautiful, like it's pure silver or pure gold or whatever. All right, and so I told you it depends on the time. It depends on the amps. So you got time, you got amps, you got moles. Remember, that's in moles of electrons. And then it also depends on the molecular weight in grams of your metal. And this is your metal, not your compound. So it's whatever you're plating. Okay, so it doesn't matter if it's silver chloride or silver nitrate or whatever, you're looking at silver. Okay. All right. So these are very simple, and I have that same thing written for you right here, so you can kind of go by it. What mass of gold in grams is plated by 25-minute flow at 5.5 amps. Okay, and remember, an amp is equal to coulomb per second. All right. In this reaction, it tells you that you're transferring 3 electrons, so that's how many moles of electrons. So the only other thing that you really have to look up is the molecular weight of gold, which is AU, and if you do, it's 196.97. So you might have to look up the molecular weight, and you know how to do that. I know you do. All right. So once you have that information, then all you do is plug and play. So I want to know how many grams of gold. So I have 25 minutes times 60 seconds per minute, and I do that because coulomb per second. And so times coulombs per second is the number of amps you have, so 5.5 coulombs per second, times Faraday's constant, which is 1 mole of electrons, is the same as 96,485 coulombs, times 1 mole of the element. Okay, so 1 mole of gold is transferring 3 moles of electrons, times 196.97 grams of gold in 1 mole of gold. And if you look back, I have canceled all of my units: minutes, minutes, seconds, seconds, coulomb, coulomb, moles of electrons, moles of electrons, moles of gold, and I'm left with grams of gold. And so I'm going to be left, when I do all that, very carefully calculating, I'm going to have 5.6 grams of gold plated on my ring or whatever I was plating. And these will be really thin. It'll be a really thin coating. And then they do some other things to make sure it won't, come off. And then they, put some kind of stuff on the outside to keep it there so you don't flake off your gold. But eventually it does. If you've ever noticed, if you have something that's plated, it eventually will kind of flake off, especially if it's like a ring or something that you wear a lot. But it takes a long time. So you can pay a lot less money for gold 5.6 grams or a plated thing than you could, 150 grams of gold in something where it's like 18 karat or whatever. That's all there is to stoichiometry of electrolysis, I'm telling you. So it's very simple. So you just have to plug it into this schematic, and then that will allow you to calculate your grams that you're plating. I'm going to show you the next one because in this one you're solving for time and you still have some to practice. But I just want to show you because I did this once before and I didn't show people and they got really confused by it. So it wants to know the time in minutes this time, okay? So we still so we got grams equals minutes times 60 seconds per minute times coulombs per second, Faraday's constant, times 1 mole of electrons per 96,485 coulombs, which is Faraday's constant, times 1 mole of element per moles of electrons, times the molecular weight of silver this time in grams per mole. Okay, so this time I'm telling you how many grams of silver you plated, and I told you what the amperage was, and I want you to tell me how long it took. So this is a great process question because if you're doing a plating or whatever and you're going to say, okay, how long is it going to take? Can I do it in one shift? Am I going to, be backed up because I'm doing it this way? I need to plate 12 grams per object, whether it's like a serving tray or whatever. The only current I can get is 3 amps. So how long is it going to take me to do that? And then you can say, okay, well, I need to invest in something where I can have higher amperage or whatever if it's going to take too long. Okay, so literally all you do is you still plug everything in, right? And you're only doing 1 electron this time. And leave the minutes as X. Okay, so your number of grams is 12 grams equals X times 60 over 1 times amps, which is 3, times Faraday's constant, 1 mole over 96,485 coulombs, times 1 mole of silver and 1 mole of electrons, because that's all we did that time. You do have to look up the silver, which is 107.8682 grams of silver in 1 mole. All right, and then you get 12 grams equals, and you multiply all that other stuff out, and you get 0.201 times X, and then you divide 12 grams by 0.201, and that gives you X, and that's going to give you 59.6 minutes, sorry. All right, now if you've got the book, the answer key says 60 minutes, okay? And that's because you only had 2 significant figures in your 12 grams. So 60 minutes. So it's going to take you an hour to do each one of those. So you can only produce 1 silver-plated tray an hour. So if you upped your amperage, then you would be able to help that a lot, right? Because you want to reduce that time, because you want to make sure that it's worth your while to do it, because you could theoretically, if everything went well, you could maybe do 6 to 8 in a shift, and that's if no problems, no personnel issues and all that, so that's not too good. Anyway, that's the practical use of this. And so then I've given you some to practice with. And that is it for electrochemistry. Thank you for being with us.